I will go through a proof of the statement that A is dense in a topological space X if and only if every non-empty open subset of X intersects A non-trivially. So we'll have to prove both directions here. So we're going to let A be a subset of X, where X is some topological space. So let's prove this direction here. So we first suppose that A is dense in X. So the definition of density, the definition we're going to use is that the closure of A, so A closure is the whole topological space itself. Now remember, the closure of A is the smallest closed set containing that set A. So you could think of it as if you take all the closed sets containing A, the smallest one would be the intersection of that collection of closed sets containing A. So the notion of smallest is via set inclusion. So let U in X be just some non-empty open subset. A non-empty. Open subset. So we're going to prove this, or we're going to prove both directions via contradiction. So we make an assumption. So we want to prove that every non-empty open subset of X intersects A non-trivially. So we can say that when you intersect A with that some arbitrary non-empty open subset, which we've defined as U, we do get the empty set for a contradiction. So if there's no intersection between A and U, then what do we have? Then A must live inside the complement of U in X. Since A is a subset of X. So if you look at this here, because we've defined U to be a non-empty open subset, so you take the complement in X, and then it must be, well, this entire set here must be a closed set. So I'll just, I guess, restate these two lines here. So it's a closed set containing A. So if we look at the closure of A, this would live inside the complement, and this comes from this result here. And then, well, because we have no intersection between A and U, so the closure of A, which lives inside here, cannot equal and must be a proper subset of X. So let's write that out. And this is because U, which was an arbitrary open set in X, was an open subset that was non-empty. So what does this imply? Well, if you look at this here, it's the case that the closure of A is a proper subset of X. Well, if it's a proper subset of X, it's definitely the case that it cannot equal X. Well, these two statements here, or these two lines, they don't pair up very well. So we have a contradiction. So our assumption that the intersection between A and U is the empty set cannot be true. So there is a non-trivial intersection. And that's it for one direction of the proof. Now we want to show that if we have every non-empty open subset of X intersecting A non-trivially, then A must be dense in X. So we suppose that the intersection between A and U, so I'm going to take U to be this here, so I'll just avoid writing it out again. It's just some non-empty open subset living inside X. So we're assuming that we have a non-trivial intersection. And again, we're going to proceed with a contradiction. So the proof goes like this. So we assume for a contradiction that, well, we're trying to prove that A is dense in X. So the definition of density requires that the closure of A is the set X. Well, they're the same sets. So we negate that and we say that the closure of A is not the set X. And what I want to define is a set. I'm going to call it V, and it's going to be defined as the complement of the closure of A in X. So V defined to be X and the closure of A in X. So it's open because if you take the closure of A, well, by definition, it's a closed set. You take its complement in X, and it must be open. So because we're assuming this, so let's write it down. So since we have the intersection of A and U being non-empty, so so U is just an arbitrary open set. Well, I'm going to shift to the set V. V is also an open set. So V must be a subset of U. So I'm just going to rewrite this as V. That's also going to have a non-empty intersection. So what does this mean? If you have a non-empty intersection between the two sets A and V, then there is some element, let's call it A in A, with A living inside the set V as well. They share a common point, and we're going to call that point A. So if A is in V, then what was V? It's this here. It's the complement of the closure of A in X. Then A must also must live inside the closure of A in X. Well, it's kind of odd to write this because, well, if A lives, so A was in A, right? And A lives in the closure of A in X. The complement of the closure in A in X. Then we have that A can't be an element of the closure of A, which is weird because the closure of A must contain A, or capital A, and little a lives in capital A. So we have a contradiction. Contradicting A, which lives in A, which definitely lives in the closure of A. Because A is, or the closure of A is, remember, the smallest closed set that contains A. So we have contradiction. So this can't be true. So the closure of A must be a set X. So that's the definition of density in X. So we've proved the statement in both directions. So A is dense in X if and only if every non-empty subset, open subset of X, intersects A non-trivially.